Welcome once again to my YouTube channel. Today we are looking into a topic in physics which is measurement of specific latent heat of fusion. In our previous class, I did an introduction on latent heat as a hidden heat. I also explained the two types of specific latent heat, where I told you that we have specific latent heat of fusion, we also have specific latent heat of vaporization. Then in that very specific latent heat of fusion, I explained it as the quantity of heat required to change a solid state of a unit mass to its liquid state or vice versa without changing temperature. So today we are to determine how to measure the specific latent heat. So in this very case, we are going to require calorimeter, the hot water, and the ice. Now let's get to the board. Let's say we have a calorimeter. Let's say we have this as a calorimeter. Normally, calorimeter will come with stirrer and also with thermometer. So we have this apparatus, then closed at the surface. So at this very point, you have to measure the calorimeter in order to obtain the mass of the calorimeter. So once you weigh it, you are going to get mass of calorimeter. So we refer this as mass of empty calorimeter. The mass of empty calorimeter. Now at this very point, you have to pour the hot water into the calorimeter. Let's say you have the hot water. We have the hot water. Now we have hot water. So here is hot water. So at this very point, the thermometer has to measure the temperature of this very hot water. Now, the temperature of the hot water measured by the thermometer will be the same with the temperature of the calorimeter. Reason is simple. The hot water and the calorimeter, both of them are in contact. Hence, the temperature of the hot water and the temperature of the calorimeter will be the same. Hence, get down the temperature of the hot water, which will now be equal to what? Temperature of the calorimeter. So we have this as the temperature of calorimeter as well as water. Okay. Now, at this very point, you have to reweigh the calorimeter again because at this very point, it contains water. So the weight of it will now increase to compare to initial weight of calorimeter. Now, when you reweigh it, in order to obtain the mass of the water added, that's the mass of the hot water. So once you reweigh it, you are going to get mass of calorimeter containing water. So we have mass of what? Calorimeter and the water. So here, mass of calorimeter plus water. Okay. Now, having obtained this, if you subtract mass of calorimeter here, it will give you the mass of the hot water. Hence, we have mass of hot water equal to mass of calorimeter plus water minus mass of calorimeter. So this gives what? Mass of hot water. So at this point, you start to add the pellets of the ice into the what? Hot water. Now, as you are adding the pellets or the pieces of ice into this very hot water, the ice will start to melt. So with the aid of stirrer, you continue to stir the mixture of ice. Look at, you have added the ice. We have the ice here. So you now see that the ice now has what? Contact with the hot water. So the ice will start to melt as it absorbs heat from the hot water as well as the calorimeter. The ice will start to melt. So it continues to melt until the whole of the ice is melted. Remember, melting takes place at a melting point. Melting point of ice is 0 degrees Celsius. So for it to have started melting implies that it has got to that very what? 0 degrees Celsius. So as it melts, its melting point is 0 degrees Celsius. So you now continue to stir it and also observe the experiment. At a particular point, you will see the thermometer, it will start increasing. So telling you that the thermometer is no longer fixed, which means the whole ice must have been melted. Because I told you that during melting of ice, the temperature remains fixed. So for that temperature to have it started increasing again means that what? The whole ice has melted. Now comes up what? Increase in temperature. So at that very point, you need to get the temperature of this very mixture. So we have temperature of the mixture, the temperature of the mixture. Remember, the temperature of the mixture is the final temperature now. So having got the temperature of the mixture, which is the final temperature, then you have to reweigh the calorimeter again in order to get the mass of calorimeter, the mass of water, and the mass of ice. So the mass of the mixture in this very case, the mass of the mixture, that's the mass of the whole of the substance, will now be mass of calorimeter, water, and what? Ice. So mass of calorimeter, water, and the ice. So with this, we can now do calculation to get mass of the ice. Hence, mass of the ice will now be mass of calorimeter water ice minus mass of calorimeter water, which is mass of calorimeter water. That gives mass of the ice. The mass of the ice. So at this point, we remember the principle of conservation of mass. Conservation simply means that what? Energy cannot be lost or gained. So it means that there is no loss of energy to the environment. So with that, the heat transferred by one substance will now be equal to heat gained by another substance. In this very case, the calorimeter and also the hot water has to transfer heat, while the melted ice and the ice in the process of melting has to absorb heat. So in that very case, the heat lost by calorimeter plus heat lost by hot water will now be equal to heat gained by melting ice, okay, plus the melted ice. Okay, so at this very point, the heat absorbed by calorimeter is mass of the calorimeter, specific heat capacity of the calorimeter, okay? Then the temperature rise, the temperature loss of the calorimeter. Let's get it again. So at this point, the heat, the heat lost by calorimeter is equal to mass of the calorimeter, the specific heat capacity of the calorimeter. Now the temperature rise of the calorimeter, the temperature loss of the calorimeter. You know the initial temperature of calorimeter is theta C, okay? Then the final temperature of it is the temperature of the mixture. So we have temperature of the mixture. Okay. Then what about heat loss by the hot water? We have mass of the hot water, the specific heat capacity of the hot water, then the temperature loss of the hot water. So we have this. What about the heat absorbed by the ice in order to melt? So the heat of the melting ice, the heat of the melting ice will now be M, mass of the ice, okay, the latent heat of the ice, which is the latent heat of fusion. You remember, the melting ice there will be no change in temperature because during the process of melting, the temperature remains fixed. So that's why we have to consider what? The latent heat, which is the heat required for that very solid to be melted. Now, the melted ice, for it to be raised to a particular temperature theta, then we have the heat of melted ice now becomes the mass of the ice, then the specific heat capacity of the ice, then the temperature rise because at this very point, that very ice has melted and the melted ice is now increasing in its temperature. So the final temperature, which is the temperature of the mixture, minus initial temperature of that very ice, and that very initial temperature should be zero because the melted ice starts from that very 0 degrees Celsius, now increases in its temperature as the melting took place at the temperature of 0 degrees Celsius. Hence, the rise in temperature starts from 0 degrees Celsius. So we have the temperature difference here. So in that very case, when we substitute all the parameters here, we are going to have the mass of calorimeter, the specific heat capacity of calorimeter, the temperature difference of calorimeter, plus here we have the mass of the water, the specific heat capacity of the water, the temperature rise, the temperature decrease of the water, which will now be equal to the heat of the melting ice. So we have mass of the ice, the latent heat of fusion. So here we have again the heat of the melted ice, which is mass of the ice, specific heat capacity of the ice, then the temperature difference. So we have to make latent heat of fusion the subject. And if you do that, you are going to have mass of the calorimeter, specific heat capacity of the calorimeter, the temperature change, then plus mass of the water, specific heat capacity of the water, the temperature change, then minus the mass of the ice, the specific heat capacity of the ice, the temperature change, then all divided by mass of the ice. And that gives a formula for calculating the latent heat of fusion. Now let's get into calculation. So the question on the board reads, calculate the heat energy required to change 0.1 kilogram of ice at 0 degrees Celsius to water boiling at 100 degrees Celsius. The specific heat capacity of water given as 4002 joule per kilogram per Kelvin. Specific latent heat of fusion of ice given as 336,000 joule per kilogram. So solution to the question, calculate the heat energy. So we are required to find H. Required to change 0.1 kilogram of ice. So we have the mass of the ice given as 0.1 kilogram at temperature 0 degrees Celsius. That's the temperature of the ice is 0 degrees Celsius. To water boiling at 100 degrees Celsius. So to water boiling at 100 degrees Celsius, that's the temperature of the water is 100 degrees Celsius. Okay? Then we have the specific heat capacity of water given as 4,200 joule per kilogram per Kelvin. Then we have specific latent heat of fusion given as 336,000 joule per kilogram. Okay? So at this very point, in order to get the very heat, now look at what to look into. We have an ice of 0.1 kilogram. Now, for this very ice to melt at 0 degrees Celsius, it has to absorb a hidden heat, which is the latent heat. After it must have melted at that very fixed temperature, now the temperature has to be raised to 100 degrees Celsius. So in that very case, we need two aspects of heat here. First is heat required to melt the ice, that is heat of melting ice, okay, then plus heat required to raise the temperature to 100 degrees Celsius. So in that very case, the heat for the melting of ice is a specific latent heat. So we have mass of the ice, the latent heat of the ice, then plus the heat required to raise the temperature to 100 degrees Celsius. We have mass of the water, then we have specific heat capacity of the water, then we have the temperature change. So in this very case now, the temperature has to be increased. Hence, we now talk about the final temperature, which is the temperature of the mixture, minus initial temperature, which will now be what? Zero. Okay? That's the temperature at which it starts to melt is 0 degrees Celsius. The temperature at which it was raised to what? To 100 degrees Celsius. So in that very case, we have the heat. The mass of the ice is 0.1. That's the 0.1 kilogram times the latent heat of ice. The latent heat or fusion of ice is given as 33600. Okay? Then we have this. Then plus, we have mass of the water. The mass of the water is the same thing as that of the ice. Why? Because it is the ice that turns into water. And we believe that there is no loss of heat to the environment. So the mass remains constant, right? So we have mass of the ice, which is 0.1 times specific heat capacity of water. We have it as 4,002. Then times the temperature difference. The final temperature of the water is 100 minus the initial temperature before the melting is 0. So we have this. So we have to add these two. Therefore, we have the heat 0.1 times 336,000. Then we are going to have 33600. Okay? Then plus we have 0.1 times 4,002, which will give 420 times difference of 100 is 100. So we have the heat given 33600 plus. If you multiply this, you are getting 42000. Now let's add it up. So we have 33,600 plus 42,000. Then we are going to have the heat equal 75,600 joule. That gives what? The value for the heat. So if what we did was able to help someone out there, please do subscribe, share, and turn on notification. See you on our next class.